So last class we worked on fit to a straight line, and in the assignment you also worked on a fit to a quadratic that involved fitting data on the expansion of the universe, the accelerating expansion of the universe, and data on galaxy redshifts and galaxy distances. Today's class, I want to continue looking at least squares fitting. I want to look at sort of a general problem of radioactive decay chains. We're going to look at the particular example of this famous decay chain that involves the subatomic particle we call a pion decaying to a subatomic particle we call a muon, which finally decays to an electron. We're going to look at that decay chain with the view to simulating experiment and analyzing the simulated experiment to extract the pion lifetime. We're sort of going to imagine that we want to measure the pion lifetime. Maybe we want to figure out how well we can measure the pion lifetime. So we're going to simulate the experiment for the pion lifetime. We're going to analyze that simulated experiment for the pion lifetime. I'll show you the case of actually an experiment that has measured the muon lifetime to very high precision as kind of a backdrop to the interest in measuring the pion lifetime. Okay, so this is the decay chain that I want to talk about. As I say, it's involves this subatomic particle called a pion that has a lifetime that's about 26 nanoseconds. So that's, you know, short on everyday time scales, but for a subatomic particle, it's kind of a fairly long lifetime. It decays to a muon. Muon has a lifetime that's about 2.2 microseconds. Again, short everyday time scales, but actually very long for a subatomic particle lifetime. And then the muon decays to an electron, which is a stable particle. So obviously that doesn't decay. This decay chain from the pion to the muon to the electron involves in each of the two steps of the decay chain the weak force. So it's the weak force of nature that causes the pion decay into a muon. It's the weak force that causes the decay of the muon into an electron. So accompanying the pion's decay into a muon is a neutrino, which you would see if you got a weak interaction, and accompanying the decay of the muon into electron is a neutrino, an anti-neutrino, again associated with the weak interaction. So this decay chain has proved important in understanding some of the basic features of the weak interaction, which is an interaction that is in some sense the most puzzling amongst like electromagnetic strong and weak interactions. So one thing that this decay chain is used for is to determine the intrinsic characteristic strength of the weak interaction. And it's characterized by a constant called the Fermi constant. And muon decay is used to determine the Fermi constant. And then once you know the Fermi constant for the weak interaction, you can then sort of calculate any other weak interactions, sort of beta radioactivity. You can calculate processes, the weak interactions in the sun that drive the sun, burning of hydrogen into helium, and so on and so forth. So that's an important quantity that's extracted from this pi mu e decay chain. Another interesting thing that this decay chain actually tells us is about what's called weak universality. So the phrase weak universality means that the characteristic strength, intrinsic strength of the weak interaction that you might see in nuclear beta decay, so in radioactive materials, is exactly the same characteristic strength that you see in processes like pion decay and muon decay, and exactly the same strength in the process, for example, in the sun, that are responsible for burning hydrogen into helium. Everywhere that we see the weak interaction, it has exactly the same characteristic strength as far as we know it. And the best test, the very best test of that, is these two decays of the pion decaying and muon decaying to an electron. So they provide the best test of weak universality. Specifically, the electrons and muons interact with the same strength through the weak interaction. The third topic that this decay chain has been sort of paramount in establishing is what we would call the kind of the form of the weak interaction, the nature of the weak interaction. It has, you probably know, a handedness to it. So only left-handed particles interact weakly, and right-handed particles don't interact weakly. Only right-handed antiparticles interact weakly, and left-handed antiparticles don't interact weakly. So what I mean by a left or right-handed particle is that if you have a particle that is spin a half, like an electron or like a muon or like an electron neutrino or a muon neutrino, its spin can point along the direction of motion or opposite direction of motion. And that's what distinguishes a left-handed and a right-handed particle. So you can think of it as electrons coming as left-handed and right-handed electrons, and neutrinos, left-handed and right-handed neutrinos. And it's only the left-handed particles that interact weakly, and it's not the right-handed particles that interact. And so that's a very characteristic feature of weak interactions. That's quite different from electromagnetic interactions, quite different from strong interactions. And that has been firmly established through this decay scheme. So it's been a quite important and interesting decay scheme. This just shows you a little bit of detail about how you get the Fermi constant characterizing the strength of weak interactions from measurement of the muon lifetime, which is this 2.2 microseconds. Basically, the top figure over here on the left is kind of what we call the tree level Feynman diagram for the weak interaction decay of the muon to an electron. And then these lower two figures here on bottom left, they're examples of higher order Feynman diagrams that contribute to the decay of the muon into an electron. So this is how we, through these Feynman diagrams, through the tree level diagram and through corrections from the higher order diagrams, would sort of picture the weak decay of the electron, of the muon to the electron, and how you would then calculate, in this kind of language, the decay of the muon into the electron. And it's through this top diagram that this relationship upstairs here emerges through, taking this diagram and using this diagram to calculate the relationship between the decay rate of the muon and the Fermi constant. So tau mu is the inverse of the decay rate, is the lifetime of the muon. And then in that equation, GF is the Fermi constant. And so you can determine the Fermi constant clearly by measuring the muon lifetime, as long as you know the muon mass over here. There is small corrections to this little equation. That's this little term over here, delta Q. These are the small corrections. These are the type of small corrections to this equation. So they come about in part from effects we talked about in the last class, that the vacuum isn't empty space. The vacuum is filled with particles and antiparticles that are appearing and disappearing. And those effects sort of dress that tree level diagram, dress it with these sort of higher order graphs here that involve really the properties, the nature of the vacuum. And so over the last, go back a couple of decades, and these quite sophisticated calculations were done of these higher order corrections, so that a very reliable relationship between the muon lifetime and the Fermi constant could be established. So they amounted to calculating that delta Q. And once you had calculated accurately that delta Q, then we're in a position where if you accurately measured the muon lifetime, you could accurately extract the Fermi constant. And by accurately, I mean the calculation, the relationship was established to some tenths of a part in a million between the muon lifetime and the Fermi constant. So if you were to make sort of a part per million measurement of the muon lifetime, you could turn it into a part per million determination of the Fermi constant. So this is how the experiment was done. It was done in quite a simple way, really. Basically, a beam of muons is directed into a target and stopped in the target. And then the decay electrons are registered in a detector that surrounds the target. And the trick here was that the beam of electrons, the beam of muons was when it's produced, a continuous stream of muons. The muon beam was directed through, it's a device that is called a kicker, but it's really like a huge capacitor with like tens of thousands of volts across the plates of the capacitor. If the capacitor's switched off, then the muons, they're charged particles, they just go straight through the capacitor. If the capacitor switched on, then the muons are deflected into a collimator or an absorber. And so remember that the muon lifetime is about 2 microseconds. So they would switch the beam on, which is the capacitor off, for a few microseconds. The beam would then pass through the capacitor, and the beam of muons would kind of load up the target with muons. And then they would switch on the capacitor. That would turn off the beam. The muons now go into the collimator. And then during that off time of the beam, they would measure the time spectrum, the decay curve of the electrons. So, it's not like you could buy, you could buy a radioactive source of cesium-137, right? Or cobalt-60. There's a famous radioactive source. You can't buy a radioactive source of muons. This is kind of preparing a radioactive source of muons. You prepare it over a few microseconds, then you take some tens of microseconds to measure the decay curve. And then they just did that thousands and thousands of times, automatically, obviously. This is just the picture of the overhead picture of this is the capacitor. And then this is the, it looks like a soccer ball. This is the electron detector. And this is just to show you 2 time distributions to give you a better idea of how it works. The top one is the time distribution of the muons arriving at the target. And then the bottom plot is the time distribution of the electrons outgoing from the target. And so in the top one and the bottom one, this far left, This is when the beam is on. So this is when the capacitor is off. And you see this high rate of incoming muons. And you see, this is like a capacitor charging up. This is the target charging up with muons. So this is preparing the source of muons. And then you switch the beam off. That's this vertical dashed line. And once you switch the beam off, downstairs here, you see the exponential decay curve of the muons in the time spectrum of the electrons. And so this is what you measure. You actually see a subtlety that they can't perfectly switch the beam off. Some muons get through, and so there's a little background, flat background of muons. There's a little flat background of electrons in this histogram. But anyway, that's basically how it's done, by making a radioactive source and measuring the decay of the radioactive source and repeating it and repeating it and repeating it. This again is the muon beamline here. Oh, sorry, the muon beamline. Muons are coming this way from top down to bottom. This was the electrostatic kicker, or basically the capacitor, the detector. And then this finally was their time exponential decay curve. We just fit it to an exponential, or they had to include a background because the turning off the beam was imperfect. They extract the time constant of the exponential. So that's their measurement of the muon lifetime. You see that it's super precise. So they determine it to a part in a million. And then that actually determines the Fermi constant to half a part in a million. The Fermi constant squared is in proportion to the muon lifetime. So if you measure the muon lifetime to part per million, you determine the Fermi constant to half a part per million. And this is the most precisely measured particle lifetime. So it's determined the strength of the weak force to that characteristic scale. The electromagnetic force is known better. So there's a constant for the electromagnetic force is known better. The gravitational force is constant for that, but that's that's much harder actually. So it's not known as well. Okay. Well, having seen how well they did the muon lifetime from that decay chain, you might wonder how well you could measure the pion lifetime, also in a similar type of experiment. So we'll simulate the pion lifetime experiment, and we'll in Python, and then we'll analyze it. We'll fit the data to see how well we can determine the lifetime of the pion. The pion is more challenging because for two big reasons. So one is it is roughly 100 times shorter lifetime. 2 microseconds for the muon is much more amenable to sort of detectors and electronics for measuring lifetimes. 26 nanoseconds is much harder for detectors and the electronics for measuring lifetime. So that's a challenge. The other challenge is that the muon decays to an electron. There's quite high energy in an electron. It's easy to surround the target with a detector and see the electrons, to count the electrons. The pion decays into a muon. If you stop the pions in that target, they wouldn't get out of the target. So it's a much more challenging experiment for that reason. Okay. Anyway, we'll simulate the experiment, and we'll fit the data from the simulated experiment using curve fit that we used in the last class for linear and quadratic fits. We're just going to use it for an exponential fit.